Hello everyone, I'm Andreas Wijaya. I'm from High Performance Computing Research Group from the Faculty of Information Technology, Universitas Kristen Maranatha. Thank you for the opportunity that I can have this presentation for you today, and I will present about quantum computing with finance application. I hope you will enjoy this presentation. Recently, quantum computing is a very hot topic in the world. And as you can see here, Google officially lays claim to quantum supremacy. That means quantum computing has a very advantage against, well, our classical computer. This is also another physicist in China. They have challenged Google quantum advantage or quantum supremacy. So this is very good topic, I think, to talk about. So what is quantum computing? Quantum computing is a computation that takes advantage of quantum mechanical phenomena in physics. At very small scales, physical matter exhibits properties of both particles and waves, and quantum computing leverages this behavior, specifically quantum superposition and entanglement, using specialized hardware that supports the preparation and manipulation of the quantum states. The word quantum itself comes from the Latin word for how much, as does quantity, something that is quantized. This term was coined by Max Planck in year about 1900. As you can see here, a very simplified diagram of an atom. As you can see here, these are orbital of electrons, and when electrons jump from this orbit to this orbit, it will produce an energy of photon, and this energy is quantized. So this is quantum computing fields. This is a Venn diagram, a rough representation of the overlapping fields. So as you can see here, big one is physics, and we have quantum mechanics as a part of physics, and quantum computing is a part of quantum mechanics. And this field, quantum computing fields, overlap with also recent trends in artificial intelligence field, which has machine learning. And we have this, the brown one is quantum AI, quantum artificial intelligence and machine learning. So this is most of the application of quantum computing. So as you can see here, the difference between our classical computing versus quantum computing. As you can see here, we have a bit. We have our computer works with bit, classical bit, which has two states only, which is 0 and 1, as opposed to quantum computing, which has quantum bit or qubit. And this quantum bit or qubit is a superposition of this both a 0 state and 1 state in the form of this superposition. You can see this is a wave function, psi, as a superposition of 0 state and 1 state, with alpha and beta as a coefficient, and this alpha and beta is a complex number. So this is one quantum computing for one qubit system. And as I stated before, that this is a superposition. Say if we have Hilbert vector space with standard basis, for example, to make it simple, we have 0 state, which has, this is 1, 0 factor, and 1 state, which has 0, 1 factor. So, and this can be superposition, like this, and the alpha and beta are complex numbers, such as the alpha magnitude of alpha square and beta square equal 1. So this is a sphere we call a Bloch sphere to represent this as one single qubit. So how we measure one qubit system? Since quantum computing follows quantum mechanics rule, so the result of the measurement is random with some probabilities. So when we measure, we only obtain one, or just like classical bit of information. So if we measure a qubit with quantum state psi, say a superposition of zero factor and one factor with alpha and beta as complex coefficient, we will get zero state with probability of alpha square. Well, this is magnitude of alpha square. And after collapse, the wave function collapse, then the psi will become a factor 0. And it will result 1 with probability of magnitude of beta square. And the new state will be psi equal factor 1. So this phenomenon known as collapse of the wave function in quantum mechanics. So this is two-qubit system. For example, if one qubit represents by 0 or 1 vector, then two qubits have four possibilities. As you can see, this is the tensor product. Say this is 0 times 0, but this is a tensor product. So this multiplication is a tensor product. And 0 and 1, 1 and 0, and 1 and 1. So we can denote this. Yeah, like this is simplification of the notation. So we have factor 0, 0, factor 0, 1, factor 1, 0, factor 1, 1. And of course, we can have superposition of these four factors like this. So we denote the coefficients with alpha 0, 0, alpha 0, 1, alpha 1, 0, and alpha 1, 1. So these four coefficients are complex numbers. And this has properties that summation, the sum of all these complex numbers squared should be 1. So suppose we have state in this superposition. If we measure both qubits, we will obtain the 0, 0 state here with probability alpha 0, 0 squared. Well, this is the magnitude of the complex number. And the new state will be 0, 0 after collapsing of wave function. And we will get 0, 1 with probability alpha 0, 1 square, and the new state will be vector 0, 1, and so on. So this is an analogous situation to what we had with one qubit, but now with four possibilities. So we can also measure just one qubit in two-qubit system. So if we have state like this, we can also measure just one qubit. So if we measure the first qubit, say the second one will be analogous, we will get 0 with probability this alpha 0, 0 square plus alpha 0, 1 square. So in that case, the new state of psi will be this form. And we will get 1 with probability alpha 1, 0 square plus alpha 1, 1 square. So in that case, the new state psi will be this. For n-qubit system, we have this form of wave function. As we can see here, there are 2 power to n terms, say from alpha 0, 0, 0, 0, 0 with factor 0, 0, 0, and so on, until alpha 1, 1, 1, 1, all 1 here with factor state factor 1, 1, 1, 1 here. So this is n-qubit system. For one qubit system, we have only 2 terms, which is alpha and beta, or alpha 0 and alpha 1 coefficient. With 2 qubit, we have 4 terms with 4 coefficients. And for 3 qubit, we have 8 terms, or 8 coefficient. And if we continue, the qubit will go exponentially as 2 power to n. Say, if we have 32 qubit, we have roughly around 4.3 billion terms. And if we have 64 qubit, we have this large amount of terms. And this is beyond simulation. And I said so because if we have small amount of qubit, it can be simulated in classical computer. Yeah, say we have very powerful computer like supercomputer, we can simulate this n number of qubit system, but not with very large number of qubit. For example, if we have 128 qubit, this is very large amount of turn, which is beyond simulation. Of course, we don't have that amount of memory. And say we have 256 qubit, this is ridiculously amount of terms. Say we have 1.16 times to 10 to the power 77 term. This is of course beyond simulation. This is close to the number of atoms in our observable universe, which is almost like 10 to the power 78 or 10 to the power 80. Well, that's approximation number or the numbers of atoms in our observable universe. So quantum mechanics tell us that the evolution of an isolated state is given by Schrödinger equation in this form. So this is the Hamiltonian and this is the wave function. For quantum circuit, this implies that the operation that can be carried out are given by unitary matrices. Like this U is a unitary matrices with properties like this. If U is multiplied with a U dagger here, U dagger is conjugate transpose, and it will produce identity matrix. So as a consequences of this operation, so we have an inverse that we call reversible computing. So these are quantum gates. We have X gate, and we have Z gate, and we have Y gate. So these gates are Pauli matrices in quantum mechanics. So this is very special gates with H or Hadamard gate in this form, 1 over square root of 2, 1, 1, 1 minus 1. This is a Hadamard gate. This Hadamard gate is special because if we apply this operation, this gate, to the quantum state, we will produce this state we will call Bell state. Yeah, this is plus and minus state. We call this is Bell state. Yeah, this is entangled state of qubits. So the other gates are rotation gates, Rx, Ry, Rg. This is rotation about X, Y, and Z axis. This is a tensor product of one qubit gate. So we can apply this tensor product, this tensor multiplication. A and B are gates, for example, acting on this multiplication or product of these two states of the qubits. So in the form of matrices, we can see the tensor product will have form like this. So this is control node or C node gate. So C node gate has the form of this matrix. It acting on two qubits, say Q1, Q0, and it will flip bit 1, bit Q1 if Q0 is 1. So why it's called control node. This is quantum entanglement. A state psi is a product state if it can be written in the form of this, where psi1 and psi2 are two states of at least one qubit. An entangled state is a state that is not a product state, cannot be factored. For example of entangled states are Bell states, like this form. Decoherence is the enemy of quantum computing. Decoherence can caused by, say, interaction of the qubits with the environment, say noise or high temperatures, and everything that can cause the loss of quantum entanglement. So to cope with this decoherence, quantum error correction is done. It can be used to prolong coherence length by correcting errors caused by decoherence. Quantum volume is to illustrate how useful the quantum computation is. As you can see here, if we adding more qubits, but the error rate is high, then quantum computing is less useful. But if the error is low, you can see the quantum volume is bigger. The more bigger quantum volume, then the more useful the quantum computation is. So here is the chart where this is limiting error rate and this is number of qubits. As you can see here, if the error rate is high, then this area is where the computation is useless because the very high error rate. But here is useful. Here is the area where we can simulate the quantum computation because the number of qubits is small. And here we will have a near-term application. This is where we are now. And here will be in the future where the useful error-corrected quantum computer can be done. This is an example of quantum circuit. So here we have a truth table, quantum truth table, and this is what we want to have. This is a quantum circuit, and this is the Hadamard gate, this is CNOT gate. So we will apply this to illustrate how to create, say, a Bell state here. So this is the algorithm. We apply this Hadamard gate to two qubits, and then after that we apply the CNOT gate. And then we will measure the result. So this is the result, which is in Bell state. This is quantum entanglement. So if we measure, then we will have probability to get this state, the 0-0 state, 50% or half. And then the 1-1 state, also 50% or half. If we run the circuit in IBM Q, this is the quantum computer made by IBM using Qiskit, the framework by IBM, we will have this result. So this is the result after we repeatedly measured, say 1,000 times. So this is the circuit. And then we measure in both qubits, say 1,000 times. After 1,000 times measurement, we will have, say, 49.3% being 0-0 state and 50.7% of 1-1 state. So this is the diagram of complexity classes. Here is the quantum complexity classes. Here is generalization of NP problems, and the small one is NP problem that can be quickly checked. And this is the PH, is the generalization of NP problem. And this is the small one, is these problems are quickly solvable by any classical computer. Here we have BQP, bound error quantum polynomial time problems, all problems that quantum computers can efficiently solve. Here there are problems that can be solved by quantum computer but not by classical computer, even supercomputer. Here we have physical technologies for quantum computers. There is a superconducting loops done by Google and IBM, and this is trapped ions by IonQ. This is silicon quantum dots by Intel, and this is topological qubits by Microsoft and Bell Laboratories, and this is diamond vacancies by Quantum Diamond Technology. This is the roadmap of Google quantum computing. Here we are when Google have hundreds of logical qubit prototype, and then in the future they will develop one long-lived logical qubit at least here, where short-lived qubits caused by decoherence. And then in the future, they will develop error-corrected quantum computing and also adding the number of qubits. This is the roadmap of Honeywell quantum computing. So you can see it's from linear until large-scale quantum computation. IBM scaling quantum technology also plan to improve their qubits, also to improve their error correction. Scaling IonQ's quantum computer is shown here. These are the numbers of algorithmic qubit, means effective numbers of qubits for typical quantum algorithm. Quantum computing has also application for financial application. From 2004, Chen, 2004, has proposed quantum binomial option pricing model. Here's the paper. And Ribbentrop et al. 2018 proposed quantum algorithm for the Monte Carlo pricing of financial derivatives. And Orell in 2021, he proposed a quantum walk model for financial option. Egger et al. 2021 Propose credit risk analysis using quantum computers. Chen et al. 2023 proposed quantum approximate optimization algorithm for financial portfolio optimization. To conclude my talk, quantum computing has the potential to revolutionize various fields including finance and bring about significant advancement in technology and society. Finally, at the end of my talk, I would like to read a quote from chaos theory in mathematics, known as the butterfly effect, that something as small as the flutter of a butterfly's wing can ultimately cause a typhoon or turbulence halfway around the world. Thank you.